I'd like to go ahead and say hello and welcome to today's e-showcase, Eliminate Class B Biosolids Handling and Disposal Challenges with Class A Solutions. I'd also like to thank Veolia for sponsoring today's event. Veolia Water Technologies offers innovative technologies and complete engineering and design of water, wastewater, and biosolids solutions for municipal and industrial customers. Today's presenters are John Orr and Eric Bergstrom. John Orr has 15 years of work experience in wastewater residuals and sludge treatment technologies and over 25 years in project and operations management. Eric Bergstrom has been a process and controls engineer at Donahue and Associates for 16 years and is currently working on his 7th biosolids drying project. And now I will hand the presentation over to John.
Thanks, Joy. These are the topics that we'd like to cover today. We're highlighting a project for the City of Wausau that's nearing its final completion. We want to present some of the challenges and drivers behind the project that Eric is going to present, and then kind of dive into the solution that was developed. Talk a little bit about the technology, the drying technology deployed in the project, and its key features and benefits, and then present what the project result looks like, how it looks installed, and then kind of go right into some of the lessons learned and in the execution and implementation, and then we'll jump into a question and answer session. So with that, I'd like to hand it back over to Eric.
There we go. Thanks, John. So I'll talk a little bit about project background here first. So City of Wausau treats wastewater from the cities of Wausau and Schofield, originally constructed in 1940 with primary treatment. So the original plant's kind of up here, pink box. That was the original 1940 construction. 1970 or so, we had secondary treatment. You can see the activated sludge basins there really well. So we had secondary treatment and the anaerobic digestion over here in the 1970s. And then 1989, we expanded that secondary treatment, added sand filter building over here, and then added sludge thickening back in the original building, which is now kind of their main building, added sludge thickening in the end of that, and dewatering up in the corner of it. So that was the 1989 expansion. At the completion of our project, the facility is going to be rated for 9.5 MGD, average flow capacity 3.58 or 35.8 MGD peak capacity, and produce nearly 2,000 dry tons annually. So solids handling pre-2020, as I kind of alluded to earlier, was the pre-digestion thickening, anaerobic digestion, and the post-digestion dewatering. And then we go to Class B land application. Kind of the missing step in there is going over to the cake solids storage building. We dewater over here in the corner of the main building, truck it around the site, and put it over in the cake building. What our project did was, among other things, add the dryer building. That's what we're here to talk about today. So now we do thickening, dewatering, and drying in that new building, and haul the product around and store it in that repurposed cake storage facility. So getting into the project, challenges included the aging infrastructure, lack of capacity in some unit processes. We've got the little bar chart there for it. Compliance concerns with phosphorus. Wisconsin is one of the states with a low-level phosphorus limit, so phosphorus was a big problem, but we're going to talk about the biosolids end of things. And then obviously here looking at the bar chart, cake cake storage capacity was a real problem on the solids end of things. There were also some shortcomings with thickening and dewatering as well. You'll note the asterisk there on sludge thickening being inadequate firm capacity. And what that means in real world terms is they had 1 GBT, and if it went down, there was problems. So the alternatives we looked at back in facility planning, these are the ones that kind of made it through to a more detailed evaluation. We threw a lot of stuff at the board at first, and these are the ones that stuck. So option 1, to paraphrase, is basically sludge drying to produce a Class A product. We'd improve that thickening because, you know, they're short anyway, improve dewatering because it's a little under capacity, add the drying facility, produce a Class A product. Option 2 is essentially T-pad, right? We're going to improve thickening, and when we improve digestion, that's what we mean. We're going to have T-pad come in for digestion, expand dewatering, store wet cake, produce a Class A product. And option 3 was essentially status quo, expand thickening, keep doing mesophilic digestion, improve dewatering, wet cake storage, a Class B product. At the end of the day, what really drove everything toward the dryer is that wet cake storage. Remember how far behind they were in that cake storage capacity? The thinking was that why continue to make and store more wet cake if we can't get rid of the product we're already making? So that's what really tipped the scales toward the drying end, is the volume reduction that could be achieved with the sludge dryer. Some of the goals as we moved into the design of the project was to design a system that was safe, reliable, cost-effective. Obviously, we have to meet permit, maximize the previous investments at the plant, right? That original construction dates back to 1940. Our project, we ended up adding 5 new process structures to the facility and reuse 15. So we had to add a few new things, but we managed to reuse the bulk of the plant. And that helps maximize the use of that existing infrastructure. So John, if you want to talk about the Veolia dryer in some more detail.
Yeah, thanks, Eric. Yeah, these are some slides about starting with the design criteria that we have in the design of our thermal dryers at Veolia. First off, they need to be, you know, safety is a key issue for everyone. The dryer has to be able to operate in a safe manner so that while operators are running it, it can be accessed, and that safety issues aren't created. Dryers are known for, in some cases, issues with dust explosions and fires and things like that. So the goal is to keep the chance of those kinds of events from happening. So the design is for inherent safety. One of the second key area is to keep implement the project and design so that it can be operated and maintained with minimal costs over the life of the project. Operating cost for operators and for any maintenance type activities, replacement of parts. So design has to be done in a way where that goal is met. The other aspect is that the components in the system are designed for longevity. So these systems are typically subject to corrosive conditions in certain areas. So the components have to be designed with the right metallurgy and capability to withstand that throughout the life of a project. Of course, the other key goal in this is energy efficiency. So the design has to be done in a way that uses minimal energy to achieve the result. This touches on a subject that we'll get into a little bit later, but this is a dryer that can be provided with add-on functionality to reduce thermal energy usage in the long run. The other aspect of the design criteria we have is But it needs to be done with proven components that have been done in multiple installations with years and years and decades of life in service. So this is the high, overview of the dryer itself. We're bringing the dewatered cake. In this case, it's about 18% solids on average, feeding it into the top of the dryer through an array of depositors, which extrude a tube of material on top of a belt. The belt runs throughout the length of the dryer. It's fed on one end and reaches a level of dryness of about 50 to 55% dry substance, and then it falls onto a second belt where the final drying occurs, bringing it up to 90% solids and higher. One thing to note: the temperatures are higher in this first portion of the dryer to drive off, the majority of the water faster, and then in the final stages, as the product is getting hotter and hotter, the temperature is moderated. This is an indirect dryer, so that all of the heating is done indirectly. We have a thermal oil system that's heated with natural gas. That oil, that heated oil, flows into heat exchangers, which the drying air is passed through. It's recirculated through a fan and pushed through the coil to achieve the temperature that's needed. And then that air is pushed essentially in a serpentine pattern up and down through this belt, and then it's recirculated. Same thing happens in the second stage, but the air in this case is taken off, and all of the water that was removed in the dryer is condensed out in a closed loop condenser and then returned here. So it's a very simple operation, very, very safe, and it runs under conditions that are very, very gentle, so that dusts aren't created. Later on, you can access a video to see how the dryer works through a YouTube link here. Some of the features of the system are that it's very robust. Historically, dryers have typically developed problems in feeding systems. We'll see in just a minute how the feed system is very robust. It's a multi-point feeding mechanism through an array of depositors. These extra depositors serve as are redundant to each other, so that if there's a problem or a blockage in any one of those, the other ones can continue to operate. The cloggage can be cleared from that one, and the dryer can be operated without interruption. It's a proven solution for some of the most difficult to dry sludges, undigested sludges. Over half of our installations here in the U.S. are working on undigested sludges. As I mentioned, inherent designed for longevity. So many of the contact parts are in stainless alloy. Inherent safety, as we'll see in just a minute, the dust levels in this dryer are extremely low. And because of the way these features combine, this dryer is highly automated. The startup can be accomplished with a single push button on a control screen. The dryer is brought up to full operation temperature and started without operator intervention. And in the same way, if an issue develops, the dryer will shut itself down. So it's kind of ideally set up so that it can be left to run on its own during evening and graveyard shifts, or even on weekends. As I mentioned, the drying air is completely recycled. This improves the efficiency, the thermal efficiency of the dryer, because we keep reusing the air. All we have to do is take out what's evaporated. It can be reused. With indirect heating, using thermal oil, this allows for a higher energy efficiency, as we can operate through a broader range of temperatures and ensure that the dryer can operate safely and with a minimal footprint or size. And as I mentioned, safety. This is a short video showing how these depositors work. This is actually a working view inside of a dryer. You see the cake is being laid down on top of the belt. The belt is very slowly moving. Those tubes of cake lay on top of each other, and the drying is accomplished in very moderate conditions. It's like squeezing toothpaste from a toothpaste tube. As long as the solids are thick enough, and generally for this type of dryer, 14% solids and higher is kind of the target. This is at the feed stage of the dryer, and then the belt traverses, moves the cake down to the end of the top belt continually. And as I mentioned, these depositors can be taken out of surface and cleaned on the fly. You simply valve off through quick connections through hoses that are connected to top. We'll see that in just a minute. The whole assembly is taken out, and there's a cleaning station provided. Normally, cleaning is done just in a matter of minutes. It's a very simple operation. You run water through the assembly, and if you need to replace a nozzle, very easily done. The dryer is operating all during this time. I mentioned the stainless parts. One of the key areas that's susceptible to damage in many systems is the belt. This belt is very robust. It's a stainless belt. It will last the life of a dryer. Once the dryer is installed and the tensioning is set up correctly on the dryer, there really is nothing to do other than to check the tensioning on the belts from time to time. Okay, let's get into some of the things that we learned in implementing this project. As Eric highlighted, the overall site, the dewatering and drying operations were set up in this building. That's a very nice layout. These are who the leads on this project were. Of course, Donahue as the engineer, lead contractor August Winters and Sons, with Myron Construction doing a lot of the mechanical work. We provided the drying system and some of the auxiliary equipment, such as the cake receiving bin, from which we pump cake through progressive cavity pumps to the dryer. Generally, those pumps bring the cake up to a manifold, which feeds, in turn, dosing pumps that feed those depositors. So we provided that. We provided all of the components of the dryer, these depositors, the belts, the place where the extraction screw where the dried solids come out, provided a crusher to reduce the size of the product so that it could be handled better for land application. The dryer accessories, such as the closed loop condensing circuit, the heating system, the thermal heating system, conveyance equipment leading to the loadout area, where product is loaded onto roll-off containers. That included the platform and filtration for collecting any dust. Anytime you move a product like this around, you'll create some dust. So we're aspirating the equipment and filtering the air that's brought in. We provided the instrumentation and controls, and then of course all of the access platforms, ladders, structural elements supporting the dryer, and those pieces. This is a depiction of the overall time frame from the start of the contract to the point where we were released to fabricate, showing the overall equipment deliveries a few months after that, and then the start of the mechanical checkout, both on the dry side and the wet parts of the system. The startup of this plant was commenced in August of last year. Was taken through its performance test in late October, and at this point we're finalizing, finishing up items on a punch list, and ensure the site is working with the DNR to ensure that Class A certifications in place on the product. Some of the things that we've learned in doing this project, of course, with folks like Eric Donahue team doing this project, who are very experienced in putting in drying projects, very helpful in every step of the way, early stages of the design and layout of the core equipment. In this project in particular, we saw almost a record installation time on the dryer itself, and went incredibly fast. And we were able to apply some learnings from other projects on this project, procedurally, in terms of our manufacturing sequence. Something that's also worth bearing in mind is the sequence of installation. There were carefully considering how equipment could be brought in and laid out. Had to be considered carefully. Of course, there are also things that learnings from limitations on storage that led us to look to consolidate as much of the equipment as possible, especially the instrumentation. This helped tremendously. Instead of having a number of separate shipments, these were all consolidated into one shipment. And then having the capability to quickly respond. In one case, we had a manufacturing defect that showed up on these hoses I referred to, the depositor hoses. So we simply replaced all of them. And we had two of them fail prematurely. We hadn't had that before, so we had to respond quickly and address the problem. So some more about the capacity. 3142 dry tons per year at 18% solids. Target evaporation rate 4,500 pounds an hour. It's using a thermal oil heated system as the primary energy delivery mechanism, heated by gas. This is a view looking on the upper platform of the dryer, the top. We provided all the equipment that you see here. This is the cake bin, or the dewatered cake is gravity fed and then pumped. This is a picture during installation, so the pumps aren't shown, but 25 cubic yard capacity, working capacity, with a lab bottom, so that the progressive cavity pumps are always, the suction is always, they're not suction starved. the goal is to keep consistent feed and pressures, cake discharge pressures throughout the system so that cake is delivered consistently, and there's no short circuiting in the solid separation in this bin. So the geometry is something that you got to take care of, especially. This is showing that same view of the dryer. It's got the array of these depositors. There are 24 depositors, and each of these depositor pumps, as we call them, is fed from this, what we call a dosing manifold, and it feeds 3 depositors. So to change one of these, to unclog one, you'd simply shut off, you valve it off, and you disconnect it and take it to the cleaning station. Very simple. And then we provided the platforms and such for the system. As far as the conveyances of the dry product, we use drag tube conveyors. That's one of our preferred means because they take very little space. They can be routed directly in an angled fashion. You can't have any too many change of planes in this, but they work very well. This is the loadout area showing the retractable spouts that are used when a truck is brought in to discharge and then aspirate through these extendable spouts to capture any dust that comes off. And that comes with a small bag filter to collect and recover any dust that's pulled through that aspiration system. This is a depiction of what the product typically looks like. This is not actually from this plant, but before and after crushing. Crushing reduces the size to a nice, very easily handled solid. And this is a shot from early January of their cake storage barn where they used to store their Class B cake. So that's the product handles very well, very low dust, and kind of wraps things up in terms of. Oh, I have one more slide. Sorry. So just to kind of summarize some of the overall features of projects like these and with this technology, that's a proven Class A performer. We've got we're now on our 11th project in the U.S. We've done projects all over the world. We've got 65 dryers installed worldwide. As I mentioned, safety is a key emphasis for us. That's why we're using this style of dryer, which has been implemented very successfully and safely in many locations. And it definitely meets Class A conditions. And it provides a safe environment for operators. And that's, of course, it's highly automated, so it can be left to run unattended. I think as we understand this staff in many cases leaves this dryer to run on its own for I think I've heard as long as 2-3 days at a time, and then low overall project lifecycle costs. So that's our final slide. So I'll hand it back over for questions.
Great. Thanks so much, John and Eric. We have lots of questions coming in, so I will get to as many of them as we can. I do want to let anybody know that if we do we are not able to get to yours, then please know that we do have email addresses here on the screen. Here's John's if you would like to reach out to him directly, but there will also be a follow-up email so we can help address any of these unanswered questions. So I'm going to go ahead and get started, and John and Eric, you can jump in on which questions you want to answer. So just going into the most recent, that was in reference to the final product. I had someone ask, the final product looks very fine in size. Is there dust issues when land apply?
Anytime you move
yep.
this,
Go ahead, John.
anytime you move this product around, you're going to have some attrition. But as it comes out, it's dust free. Dust free means generally less than 3% after by weight of the crushing step. So Eric, you were going to add something to this, or?
Yeah, well, kind of expanding on your point, John, I would say every time you handle a dry product like this, you're going to create some dust. I would not say that it is problematic. We anticipated there being some dust creation. That's the downside of storing in a cake barn like we did, right? We're going to haul it over there, we're going to dump it, then we're going to pick it up and load it back on a truck. So every time we handle it like that, we do create dust. It has not been problematic thus far, though.
Thank you so much. And I will go back towards the top here a little bit. With PFA's regulations on the horizon, how does your system handle that?
So I'd be happy to address that one. This the system is done in a way where using thermal oil as the primary heating media, we have a feature that we can add on to this drying technology. It's called ERS. It's been around since 1995, and ERS stands for Energy Recovery System. Its primary purpose was to recover energy by taking and combusting those dried solids coming off the process. And that temperature, it's done with a small combustor, a small sliding step grate furnace. And we can operate that furnace at a temperature range where we can get a maximum decomposition of PFAS compounds. That's above 1,000 degrees Celsius, generally close to 2,100 Fahrenheit is the target operating range. But anyway, this facility was laid out with the potential option to add that functionality in the future. So it's all possible because we use thermal oil. That's the media that we recover heat off the back end of that process and return it for use in the drying stage.
So with regards to the PFAS issue there, some other thoughts on that. Generally speaking, sludge drying is not going to handle PFAS, right? It doesn't get hot enough. Even if you go to a high temperature drum dryer, it doesn't get hot enough. If you want to deal with PFAS, you need to do incineration, pyrolysis, gasification, something along those lines. For Wausau in particular, PFAS is being handled more on the source side. Donahue is designing a PFAS filtration system for their water utility. The bid set for that just actually printed yesterday. So we're doing a granulated carbon absorption system on the drinking water. So we're hopefully going to get the PFAS out before it makes it to the wastewater and our dryer.
Thank you so much. And then I will ask, can you talk a little bit more about how this dryer can operate without the operator attendance?
Yeah, I can take that, Eric. That's largely because the dryer is highly automated, and it runs in a fashion that is very controllable. Without interruption, the system can be run and start up, shut down, and it will shut itself down. It'll put itself into a very safe operating mode if there are any events that occur during unattended operation.
Thank you. Another question. Does the system ever become energy neutral? For example, energy in equals energy recovered.
Yeah, I could touch on that. As Eric mentioned, this is simply as a dryer, operating as a dryer. The whole purpose to get into an energy neutral condition, you've got to look at recovering energy from somewhere. So with this dryer alone, it can be functionality can be added to recover energy from the dried product through a combustion process or incineration. But as the dryer by itself can't reach an energy neutral state without some kind of energy recovery.
And someone had asked, what is discharge pressure of PC pumps typically?
The cake pumps from the pumping up from the cake bin that we looked at generally are normally running 90 to 120 pounds, but they're capable of running much higher, if need be. But that's a normal kind of design pressure.
System design is 350 psi.
Yeah. And then what sensors and safety features will shut the dryer down?
So clearly we're watching temperatures, continuously watching temperatures. Any temperatures either in the product itself or in the air recirculating within the dryer, those will trigger shutdowns. Loss of suction pressure will stop feeding. Of course, we've got the thermal heating system itself has a number of safety features that prevent it from operating under unsafe conditions.
Well, John, the one we're looking at right now with the slide up is, you mentioned temperature in the dryer. There is a deluge spray system inside the dryer. That's that blue water piping there. So if temperature gets too high, we will spray the dryer with water.
Yeah, that's definitely a feature that's included in all these dryers that we furnish.
Thank you. Let me move to a more recent couple questions. What is the smallest size plant practical for your system in dry tons per day?
I'll say that corresponds to on the order of about 5 mgd, which translates to about typically 5 to 7 dry tons a day, kind of in that range.
And then I had a couple people refer to this question that was asked, what is the residence time in the dryer?
Yeah, from start to finish, the typical residence time is about 90 minutes for the solids throughout.
And then what experience do you have in drying sewage sludge in the U.S. or elsewhere?
So yeah, Veolia as a company here in the U.S., we've got 11 projects that have been completed or are in the final stages of execution now. This is 13 dryers in total, and then worldwide we've got 65 dryers installed, dating back to 1995.
Perfect. Thank you. Let me go back up towards the top. So this was closer to the beginning of, or your part of the presentation, John. What is measured product bulk density?
That's a great question. Before crushing, it's typically on the order of 12 to 15 pounds per cubic foot. Some of the K characteristics affect that. But after crushing, we typically will see the density, bulk density increase from typical range of about 22 to 27 pounds per cubic foot.
And then this goes back to referencing about the temperature, but how hot does your process building get in the summertime? Do you need AC in the building?
So this room is not air conditioned. It is just one air change an hour type ventilation. So not a lot of heat coming off the dryer. Most of the heat is recirculated within the cabinet. We're not just, you see that cabinet on the screen right now, that's a whole insulated box. We're not ejecting a lot of heat to the room.
Is the feed sludge Class B prior to the final product?
Yes.
Thank you. And then let's go back towards the top. What percentage by mass is removed as dust with product loadout and dust filtration, and what particle is defined or measured as such? Less than 0.5 millimeter. That was the example.
Yeah, so I don't know that we've measured it at this plant, but from the pictures, the final picture, the dust collection is done in a way where it's discharged into single 55-gallon drums, which are occasionally changed. So depending on how the sludge behaves, it's generally going to be by mass under typically 2 to 3% below what at that threshold that one would consider it to be a dust. So I don't know if that answers the question very well, but by mass, it's generally under 3%.
Thank you. And then I think we have time for just one more question. So before we get wrapped up here, but how do systems using thermal oil for heating compare to those using steam or hot water for heating?
Well, there's a lot that could be said about that question. Thermal oil is known for being an efficient way to heat systems, and it's been used in many places. It's a safe way of heating. In this application, we're heating indirectly, and it's operated under conditions where it will not immediately vaporize if there's a leak, and it's well below its flash point. So flash point meaning the temperature at which it would catch on fire. It's well below that condition. So from that point of view, there's an inherent safety. Also because the temperatures can be controlled safely, and there's a flexibility to running at a wider temperature range. You have more flexibility in the way thermal oil system can be operated. It doesn't generally require a licensed operator to operate. Some hot water and steam systems, just depending on the location. Some states require that a licensed stationary engineer operate those. So there's some advantages. Also, in this case, it allows for pretty nice level of automation. You don't have to worry about water treatment. The oil is initially charged into the system and runs for years. And you send out you'll take a sample of it every year, and the oil supplier will check the condition of the oil. Most systems you never have to do any replacement of oil. You just add additional oil from time to time.
Couple other thoughts on that, John. So when you talk about thermal oil versus hot water, say, or steam for it, this is always something to talk about with clients about when we start talking about dryer projects with them. Their preferred heating medium. So you got a few options there. On the water side, you got low temperature water, kind of your conventional plant heating water loop, 180 degrees Fahrenheit, say, top end, 180, 160 degree loop. Right? Problem with that is the relatively low temperature. So if you're going to run a dryer off it, it ends up being a very large dryer. You don't have that driving force to push heat into the sludge. You can step it up to a medium temperature water system. That'll start getting you up into temperatures that are comparable to thermal fluid, 200s, 300 degrees. But you have to pressurize that system. You're operating above the boiling point of water, so you have to charge it to, say, 50, 75 psi to avoid that phase change, right? Then the risk is if you were to have a leak in the piping, it's going to flash the steam on you, and a lot of folks are uncomfortable with that thought. Same goes for steam, too. A lot of wastewater plants are not used to dealing with steam, and there's safety concerns with that as well for a lot of folks.
Thanks for adding that in. We are at time, so I do want to take just a moment to thank both you, John, and Eric, for a great presentation. I'd also like to thank Veolia Water Technologies for sponsoring today's event.